Hello, everyone. Today we are going to talk about exponents and radicals. To start, we are going to give basic definitions. So what is a to the power of n? Actually, a to the power of n, which is like about exponents, it's number a multiplied by itself n times. So I'm going to write it down like this and label there are n a's. N is a natural number. For example, we can have 1 over 2 to the power of 3, means that it's 1 over 2 by 1 over 2 by 1 over 2, which is going to give us 1 over 8. Okay. A to the power of 0 is equal to 1. That's going to be by definition. For example, 5 to the power of 0 equals 1. So now n is not just natural, but also can be a whole number, right? What are we going to do with, integers? Integers are whole numbers plus negatives. Let's define what is a to the power of negative 2. A to the power of negative 2 is actually 1 over a squared. So when we have a minus in front of a power, we're going to understand it as 1 divided over a to that power. For example, 2 to the power of negative 3 is 1 over 2 to the power of 3, which is going to be still 1 over 8. Okay, what are the rules for exponents and radicals? Let me kind of make it a little bit bigger. Let's talk about rules. So we are going to start with rules of addition of powers. If you have a to the power of n multiplied by a to the power of m, a here is called base. Let me write it down. A is base. And n or m are exponents. So if two numbers have same base but different exponents, you can actually add them. And that's going to give you the final number a to the power of n plus m. How do we explain it? Why we can do this? Well, a to the power of n is going to be what? N times a, right? N times. And a to the power of m is going to be a multiplied m times. So this one is m times. So all together, we are going to have n plus m times, right? So all together is n plus m times, which is going to give us a to the power of n plus m. For example, 5 to the power of 2 by 5 to the power of 3 is going to be 5 to the power of 2 plus 3, or 5 to the power of 5. Okay. Okay, next, division of exponents. Let me scroll a little bit up. And the next rule, rule number 2. What if we divide exponents? Well, let's first kind of consider what happens and then give general formula. So what we have over here, n times a, right? A multiplied by a, and we have n times. In denominator, we have a multiplied by a, m times. We know that we can cancel all this m, like we can cancel this one, and we can do cancellations until we cancel the last one. If n is bigger than m, the resulting number of a is going to be what? A to the power of n minus m. So it's kind of, we cancel m of them. We cancel this one. Well, maybe we had over here one more, and we cancel this and this, like we cancel all of them, but we still have a little bit more over here. Well, it's not always going to be a little bit more. It can be a little bit less. That's just going to give us a negative number. So if we have less, we are going to kind of get a different cancellation. Let me show you an example of how the rule is going to work. And there are going to be two examples. Example number one. Well, we have, for example, 5 to the power of 3 over 5 to the power of 2. What we have? 5 by 5 by 5 here, right? And over here, just 5 by 5. We cancel this, and this, and we have 5, right? Which is actually 3 minus 2 equals to 1, right? Example number 2. What is going to have if we have opposite situation? 5 to the power of 2 over 5 to the power of 3. Can happen. Nobody tells us which one's supposed to be greater, right? We have 5 by 5 here and 5 by 5 by 5 here. We start cancellation. We actually cancel everything in numerator, but there is still 5 in denominator. So we have 1 over 5. We remember 5 in denominator can be represented as 1 over 5 to the power of 1 or 5 to the power of negative 1. But if you consider the powers over here, you can write it down as 5 to the power of 2 minus 3. And that's exactly going to be 5 to the power of negative 1. So formula actually works not only for cases when n is greater than m, also works for cases when n is less than m, and we have more numbers in denominator than in numerator. Okay, rule number 3. Rule number 3, give me a second, is going to be power and power, like a to the power of m, and then you take it to the power of n. Here, guys, I don't want to make it general consideration. I want to consider example first and give you the final answer after, okay? Consider example 5 to the power of 2 and then to the power of 3. We remember that raising to the power of 3 is going to be repeating the number which sits in a power like a base 3 times. So it's 5 to the power of 2 by 5 to the power of 2 by 5 to the power of 2. Each 5 to the power of 2 is just 2 5s multiplied, right? It's 5 by 5, and again 5 by 5, and again 5 by 5. So in total, we have 6 5s, which is kind of result of multiplication 3 times. And there are 2 5s for this power. So it's 3 by 2. So we are going to have 5 to the power of 6, which is 5 to the power of 3 by 2 or 2 by 3. So the rule is going to be when you raise power to the power, you actually multiply powers like this. And it doesn't matter, you multiply n by n or m by n. You can put them in any order. We remember that multiplication is commutative. Okay, next rule is going to be distribution of a power. Rule number 4, a multiplied by b to the power of n. How do we distribute the power? Well, I'm going to give example first, and then we are going to make a rule. Imagine that you have 5 multiplied by 2 to the power of 3. Remember that power of 3 means that you repeat the base 3 times. So it's 5 by 2 multiplied by 5 by 2 and multiplied by 5 by 2 and like 3 times. You see that in this product, we have 3 5s and 3 2s, right? So for us, it's going to look like we just distributed this 3 over 5 and over 2. So the rule is going to be next. The product to the power of n is going to be the product of each of the factors to the power of n. Okay. Okay, good. Next, we are going to consider self-solve problems. Guys, I'm going to put several problems on the board, like actually 6 problems. And I'll ask you to work on these problems for like 10-15 minutes. So stop my video and then work on the problems. And then restart it again and see what are the solutions. I'm not going to make a 10 minutes pause in the video. I'm just going to start it after like 3 seconds, but you can always stop it and kind of work on the problems yourself. So I'm going to put them in green, self problems. Sorry, self-solve problems. 15 minutes is supposed to be enough, but you can take more time, you know, when you are watching it, you can make it longer or shorter. So I'm going to start, sorry, problem 1. In all problems, I want you to multiply, simplify, do your best on using the rules we have, okay? So here, for example, I want you to simplify it. And the next problem, just going to be rule by rule. 3x to the power of 3, open parenthesis, simplify. Problem 3, x over 3 to the power of 2, also open parenthesis, simplify. Let me scroll it a little bit higher. Problem 4 is going to be kind of simplify expression. Sorry, I'm looking at the notes to not miss powers. So I'm going to be quiet for a while. And problem 5, x over y to the power of 2 by x multiplied by y to the power of 3. So it's product simplified 2. And problem 6. Right now, problem 6. Last problem in this assignment. 3x to the power of negative 2 divided over 9x. Simplify. Okay. So guys, you can stop your video, start working on the problems, and then turn it on again and see how solutions are going to look. I'm just going to make a short pause, like 2 seconds, and then count 1, 2, 3, and start solving them with a different color. Okay. So 1, 2, 3, and I'm going to start solving them. And you can always check what solutions you are going to have in comparison to mine. So here we have same base and different powers. We are just going to subtract them. Well, we're supposed to add them, but adding -7 is subtracting actually, and 4 minus 7 is -3. Do you need to write it down as 1 over y cubed? Well, for my class, it's not necessary, but maybe in the book, the homework is going to ask you to write it down without minuses, okay? So problem number 2, we distribute the power of 3. So it's 3 to the power of 3 by x to the power of 3. And 3 to the power of 3 is 27, and x to the power of 3 is just x to the power of 3. Here we are going to distribute the power over the fraction. Well, fractions are like same as product. If you wish to do a little bit more steps, you can represent fraction as a product and then distribute the power. Otherwise, you can just distribute the power. So I'm going to do extra step, but it's not necessary to do. So I'm going to represent it as product, x multiplied by 1 over 3. Now I put the second power over x and over 1 over 3. Sorry, accidentally my second power turned into a third power. So x squared is x squared, right? But here 2 is going to mean that it's 1 over 3 multiplied by 1 over 3, which is going to give us x squared over 9. And if you distribute the power right away, you are going to get the very same answer. So my suggestion is to not do these extra steps, just distribute the power. Here, guys, I'm going to first open parentheses and then count what I have in numbers and a's and in b's. So 2a squared b cubed, right? When I open parentheses over here, I'm going to distribute 2 over 3 over a and over b squared. So it's going to be 3 to the power of 2, a to the power of 2, and b squared to the power of 2. Now, I'm going to count how many of everything I'm going to have, but before I'll simplify this. Remember, power and the power, it's actually a product of 2 by 2. In our case, it's going to be b to the power of, sorry, my pen stopped working. Come on, b to the power of 4. Oh, maybe I pressed something wrong. It's very strange. Okay, guys, give me a second. We'll get the pen back. Oops, my computer is not working. Yeah, guys, I had a little problem with my computer. Somehow it stopped recording for a second and kind of was not working. So I'm going to just fix everything, whatever was missing. So we have b to the power of 4 here. 2 by 2 is 4. So I'm going to count all a's I have and all b's. First, let's see what we have with numbers. And we have 2 and 3 to the power of 2, which is 9, right? 2 by 9 is 18. What else I have? I have a square and another a square. So I add 2 and 2. I'm going to write down a to the power of 2 plus 2. What I have with b's? Well, that's a cube, right? And this one is b to the power of 4 because we had that 2 to the power of 2. So what is going to be my final answer? I'm sorry, I'm going to place my final answer here. It's 18, a to the power of 4, right? 2 plus 2 is 4, and b to the power of 7. Okay, very good. Now let's move to our fraction. I'm going to open all the parentheses over here. Now, guys, I'm not going to do extra steps. I'm just going to distribute the power over numerator and denominator. So it's x squared over, over y squared. And here I distribute power of 3 over each factor, x cubed and y cubed. Now I'm going to combine the powers. So I'm going to put x and see that power here is 2 and the power here is 3. So I add them up. And then y, and the top power is 3. And the bottom power is 2, which is subtracted from the top one. Remember, canceling numerators and denominators. So what we have, x to the power of 5, 2 plus 3, right? And just y, because 3 minus 2 is 1. I can put 1 here, make it more transparent. And the last problem, problem 6. Probably a little bit more complicated. In problem 6, we are going to distribute first power of -2. Or maybe, yeah, let's do it. So it's 3 to the power of -2 and x to the power of -2. And here 9 and x, right? Now I'm just going to combine powers. Well, guys, 3 and 9 are kind of have different base, right? But I always can represent 9 as 3 squared. That's what I'm going to do. I'm going to write down that 3 over here is -2, and then the power of denominator is also -2, right? We remember that it's n minus m, the top minus the bottom. For x, I have -2, and x from denominator is another -1, because the power of x is 1 over here, right? So now I'm just going to combine the powers. So it's 3 to the power of -5, -4, sorry. -4 and x to the power of -3. If you don't want to have negative powers in your final answer, you can always put them down and write down that it's 3 to the power of 4 by x cubed. And if you know what that 3 to the power of 4 is 81, you can write down that it's 1 over 81x cubed. But again, it's not necessary. You can leave it as it is, or with negative powers. For me, it's the same. Okay. Very good. Let's talk now about scientific notation. Scientific notation is a convenient way to represent numbers with exponents and making our life a little bit easier when we have to multiply them or divide them or use a calculator. So let me scroll this up and kind of scientific notation. Give me a second. So what is a scientific notation? What is scientific notation? Scientific notation is representation of number x as number a multiplied by 10 to the power of, let's say, n. What are the rules? The rules are that your a is supposed to be between 1 and 10. Well, I think it's supposed to be less than 10. I would not suggest you to use 10, actually. I would say that it's strictly less than 10. So number between 1 and 10, and n here is integer. Integer means that all numbers which we use for counting 1, 2, 3, 4, 5, 0, and -1, -2, -3, -5, and so on. For example, if you have number a which equals 0.001 0.0035. How to represent it in scientific notation? To represent it in scientific notation, we'll need to first represent it as a product, right? What we can do here, we can move decimal point by 1, 2, 3 positions to the right. When we do this, to not change the number, we're supposed to multiply by, or kind of multiply by 10 to the negative 3. So I'm going to write down 3.5 by 10 to the negative 3. And this is kind of scientific notation. Why it's 10 to the negative 3? Well, actually, if you write it down like in without minuses, it's going to be 3.5 or 10 to the power of 3, or 3.5 over 1, 2, 3 over 1000. Division over 1000 is moving the decimal point 3 places to the left. So it's supposed to be like, let me write down 3.5 and 3 places, 1, 2, 3. So point is going to be here. And that's exactly the same number we had over here. So, well, we know how to represent scientific notation when it's a very small number, right? You move your point to the right, decimal point, and count how many places you go. And then put this number of places, like 3 places, to the negative power of 10. That was example number 1. Example number 2, if you have A equals 3500. Well, it's not in scientific notation, right? Just because your number is not between 1 and 10. But what we can do, we can put a decimal point 3 places to the left, right? We can write it down as 3.5. To keep the number, we are going to multiply it by 1000, because if we multiply 3.5 by 1000, we are kind of moving the point back, right? But 1000 is what? 1000 is 10 to the power of 3, right? Because 1000 is 10 multiplied by 10 multiplied by 10. And we got scientific notation again, just the opposite exponent. Okay. Well, we know how to write down how to go from normal numbers to scientific notation. Now, how do we go back from scientific notation to just regular number? Example number 3. Let's consider scientific notation. 4.36 by 10 to the negative 2. What kind of regular number it's going to be? Well, remember, 10 to the negative 2 was moving the point 2 spaces to the right. Now we're supposed to move it 2 spaces to the left, back 1, 2. And the point is going to be here. So we're going to write down 0.0436. That's how the number looks in normal way. And this is scientific notation. Example number 4. Imagine that our number is now 357 to the power of 10 to the power of 2. So how do we write it down in normal as a normal number? Well, we know that 10 to the power of 2 is actually moving the point 2 places to the left. Now we're going to move it 2 places to the right back. And we get 357. That's our normal number. Okay. Now, why do we need scientific notation? Well, we are going to start doing calculations, multiplying, dividing, raising to the powers, extracting roots from complicated numbers, which are kind of long and can be very big numbers, very small numbers. And it's not going to be very convenient to enter like 0.000025. It's going to be much easier to write down 2.5 by 10 to the negative 5. Just count the zeros, okay? Especially in calculator. So we needed to calculate faster. We needed calculate faster. I'm going to consider an example. Let's imagine somebody is asking us to calculate the volume of something. Remember, volume is a product of the sides A, B, and C, and somebody is giving us sides. Side A is 0.0035. Side B is 0.002. Well, I think even 3 zeros. Let me put more zeros. Sorry. 0, 2. And side C is 0.01. You see, numbers are small. You can represent each of these numbers in scientific notation. So let me use a different color. So for example, for this number, we'll need to shift decimal point 3 places, right? So it's 3.5 by 10 to the negative 3. Here, 1, 2, 1, 2, 3, 4, actually, 4 places, right? Because 2 is a number between 1 and 10. So we're going to write on 2 by 10 to the negative 4. Again, when you go to the right, it's going to give you a negative power. And the last one is going to be just 1, 2, right? So it's 1, 10 to the negative 2. Again, our number here is supposed to be between 1 and 10. Between 1 and 10. Okay, now I'm going to substitute them into the formula and calculate the volume. You see how fast it's going to be. So 3.5 by 10 to the negative 3, by 2 by 10 to the negative 4, and by 1 by 10 to the negative 2. First, I'm going to multiply all the numbers. 3.5 by 2 and by 1. And then I'm going to calculate the power of 10, minus 3, minus 4, and minus 2. So what I have in total, 2 by 1 is 2, right? 3.5 by 2 is going to give me 7. And the net power is going to be 3 minus 4 is minus 7, minus 8, minus 9. So minus 9, that's final answer. And this answer, if you write it in a regular form, is going to have lots of zeros. So I'm going to write it down. That's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 7. It's not very convenient. It's much like more complicated if you write it down like this, right? Okay, so we're kind of done with scientific notation. Please use it whenever you can. Now I'm going to move to radicals, like our next of the lecture is going to be about radicals. So, well, let's start with definition of what is a radical. And let me change my color. First, we are going to start with just a square root of a. Square root of a equals b is equivalent to say that b squared, that's a number which is a result of square root, is equal to a. So if you extract the square root of 4 and say that it equals to 2, means that you take 2, raise it to the second power, and get 4. We are going to put some restrictions on b for different powers. But for now, I'm just going to give you example. Square root of 4 equals 2 means that you take this 2, put in a second power, and get 4. Okay. Well, the fourth root of 81 is going to be what? It's going to be 3. Why? Because you take 3 multiplied by 3 multiplied by 3, you are going to get 9 by 9, which is 81. So 3 to the power of 4, 3 to the power of 4 is equal to 81. Okay. More examples, and then more stricter definition. Cubic root of negative 8. What is cubic root of negative 8? Well, what we need to multiply 3 times to get 8? It's 2, right? But to get negative 8, it's probably negative 2. I'm going to write down negative 2 and kind of show that negative 2 to the power of 3 is negative 2 by negative 2 by negative 2. So you multiply 2, so you get 8, and multiply minuses. These two minuses are going to give us plus, and the one left over minus is going to give us minus. Okay. Well, guys, I would say that you see that when you deal with minuses, even amount of minuses is always going to give you plus, right? So if you have even power, the even root is going to always give you a positive number. For odd powers, you can have a like positive or negative number as a result, depending on what sits in your under the root. Okay, now let's talk about rules. Well, there are certain rules, and they are very similar to the power rules. So too big. Let me make it a little bit smaller and start with rule number 1. Rule number 1 is nth root of the product of a by b. Well, we can distribute it into the nth rule of A and nth root of B. For even roots, for example, square root of A is A square equals absolute value of A. I'm trying to say that what can happen, guys? You can have -2 and you can square it. It's going to give you 4, and you can extract a square root and you are kind of supposed to get 2. But if you just cancel the square root and the square, you are going to get -2. You remember that even roots are always going to give you something positive as a result, just because you cannot multiply even amount of numbers, negative or positive, and get something negative. Okay. Rule number 3. Nth root of the fraction. You can distribute the root. It's nth root of A and nth root of B. Okay. And the last rule, I'm going to give examples on all these rules. Just like, let me write down the rules. If you have a root of a root, well, guys, this is going to look like a power of a power. Remember, we multiplied powers. We are going to do same with the roots. So we multiply roots and we put them like multiply indexes, and we put them like a new index for A. Okay. So I'm just going to consider a couple of examples of use of these rules. So let's consider example 1. 4th root of 16 over 81. I'm going to use rule number 3. 4th root of 16 and 4th root of 81. Well, I remember 16 is actually 2 by 2 by 2 by 2, right? And 81 is 3 by 3 by 3. Sorry, wanted to write multiplication and 3 at the same time. 3 by 3. So we are going to kind of have 2 over here and 3 over here. I want to write down a general rule, and maybe I should not write down over here like the second power only. Let me erase the second power here and the second power. I'm going to rewrite it for nth power. So it's nth power of A to the power of n equals absolute value of A when n is even. And it equals, let me erase actually and write it down like this, absolute value of A, and equals A when n is odd. Better. Okay. Okay, example number 2. Example number 2, cubic root of a square root of 32. Well, according to our rule number 4, we're supposed to multiply 3 and 2 and get 5 and get 6 of 6 root of 32. It's not going to be anything nice. I think 5th root of 32 is going to be 2, and 6th root, why don't we change it to something nice? I'm going to put 64 over here, okay, guys? Then it's gonna look nice. It's 6 root of 64, and I think that's supposed to be 2. Yeah, you multiply 2 by 2, it's 4, multiply 4 by 4, that's going to give you, well, let's do it this way. The second root of 64 is 8, right? And cubic root of 8 is, and cubic root of 8 is 2. Okay, I'm trying to explain why it's going to look like 2. Okay, example number 3. Example number 3, more complicated expression, a cubic root of 27 multiplied by x to the power of 6 and by y to the power of 2. It's going to be a cubic root of 27, a cubic root of x to the power of 6, and a cubic root of y to the power of 2. Well, guys, for 27, it's 3 multiplied 3 times. So it's actually 3 cubed and the cubic root. We remember that by the rule over here, by rule number 2, it's going to be equal to just 3. Here, what is x to the power of 6? X to the power of 6 is x to the power of 2 to the power of 3, right? Well, because I'm planning to use rule number 2, I'll need the same power as a root index. Remember, 2 by 3 is 6, so that's going to be the case. So here, when we cancel or kind of extract a cubic root from a cube, we are going to have x squared. And for the last term, nothing is going to happen. That's going to be just a cubic root of y squared. So we have 3x squared, a cubic root of y squared. And that's going to be the final answer. Okay. Let's talk about rational exponents. Rational exponents are more complicated. Let me use a different color. Use blue. Rational exponents. The rational exponents. Well, for example, we have the cubic root of y to the power of 2, and we cannot kind of extract it because we can extract a cubic root of cube, but not a cubic root of second power. Well, we are going to introduce rational exponents. A to the power of 1 over n is going to be nth root of a. We'll kind of represent the root radical in exponential notation. So we have exponent, but exponent is a little fraction, 1 over n. So then a to the power of m over n is going to be either nth root of a to the power of m or nth root of a to the power of m. You can kind of switch them. So the top is going to be the power, the bottom is going to be the radical index. Okay. And we are going to consider that if n is even, then 8 must be greater or equal than 0. We're not going to extract roots from negative numbers. Okay, I'm going to consider a couple of examples. So example number 1, 8 to the power of 2 over 3. What is it? Well, you can either represent it as a cubic root of 8 squared, which is going to be what? Cubic root of 2 by 2 by 2, it's 8, right? And when you square it, it's 2 by 2 by 2. And here what we can kind of think about this, 6 times 2, right? Or we can write down that it's 2 squared cubed. Well, it's 6 times 2, right? When we extract a cubic root out of cube, we are going to get 2 to the power of 2, which is 4. You can also represent the very same number, 8 to the power of 2 over 3, as cubic root of 8 squared, which is easier, right? Cubic root of 8, we know that it's 2 to the power of 3, so cubic root is going to give us just 2. 2 squared is going to give us 4. Same answer, different ways to represent. Again, there is no preference. Next example, example number 2. Example number 2, sorry. Example number 2. 2 to the power of 1 over 2 divided over 2 to the power of 3 over 2. Let's simplify this expression. How we simplify it? We write down 2, the base. Base is same for both expressions. And then we copy the power. From numerator, it's going to be power positive. From denominator, it's going to be negative, right? And then we just work with the power as general fractions. So we have 1 minus 3 over 2. Common denominator is 2, right? And 1 minus 3 is what? Negative 2 over 2. And then we continue working with the power. And 2 over 2 cancels, and we get negative 1, which is going to give us 1 over 2. And that's going to be our final answer. And I know that it's very, very long lecture, but the last topic of this lecture is rationalizing denominators. Okay, let me scroll it a little bit higher. And we're going to talk about rationalizing denominators. What means rationalizing denominators? Well, usually it means that you don't want to have any radical expressions in denominator, anything weird. You just have normal numbers, like you're not going to have square root of 2 in denominator, but you want to have 2 or 8 or whatever. I'm going to show you several ways of doing this, and they are going to depend on the power of denominator. For example, if you have expression b over square root of a rationalizing denominator in this case is going to be multiply your fraction by square root of a over square root of a. We remember that this is 1, so it's not going to change our fraction. But what we are going to have this way, b square root of a over square root of a multiplied twice, right? We remember when we square the square root, we are just going to get the expression from under the square root, and we are going to have a. It's not like this expression is better than this one, but it's rationalized. We don't have anything like radicals or weird exponents in denominator. So I'm going to consider several examples. Example number 1. Well, for example, 5 over square root of 2, rationalize. We multiply over square root of 2 and square root of 2, which is 1, right? And have 5 square roots of 2, and here they're going to make up 2. More complicated example. What if the root is not a second root? What if 5 over cubic root of 2? Well, remember, guys, to eliminate a cubic root, you will need to cube it. So if you just multiply by cubic root of 2, you are going to square it. I'm going to write it down. If you just multiply by cubic root of 2, numerator and denominator, you are going to square it because it's 2 of them, right? So you are squaring them. It's not going to help us because a cubic root can be eliminated only by cubing. So I'm going to multiply by 1 more cubic root of 2. Now, what I have a numerator, 5 and the cubic root of 2 squared. And in denominator, I have 3 square cubic roots of 2, right? Cubic root of 2 cubed. I remember that cube and cubic root are going to cancel each other and give me just 2. In numerator, what I'm going to do, guys, it's not necessary to do, but to simplify this expression, I'm going to switch the cube and the square. I'm going to write it down like this. A cubic root of 2 squared. I always can do this, right? In denominator, it's just 2. I know that 2 squared is 4, so I have 5 cubic root of 4 over 2. And kind of mathematicians sometimes think that it's better than the previous expression. Though for me, it's the same. Well, example number 3. What if we have 5 over cubic root of a squared? Well, now that's not a number. It's just like a variable. What are we going to do, guys? I'm going to teach you how to deal with any power of denominator. First, write it down as rational exponent. A 2 over 3. Remember that the root always comes in denominator. Now, look what is missing here to turn the power into 1. So we have 2 over 3. To make it 1, we'll need 1 over 3, right? If we add 1 over 3 here, we are going to turn it into 1. So what I'm going to do, I'm going to multiply it by a to the power of 1 over 3, numerator and denominator. So what I have in numerator, 5a to the power of 1 over 3. In denominator, I'm going to have, by adding the powers, 2 over 3 plus 1 over, sorry, kind of 2 instead of 3, 1 over 3, which is going to give me, well, this is a cubic root of a, right? Cubic root of a. And in denominator, I'm going to have just a to the first power. Well, you can write down just a, right? Because it's 2 over 3 and 1 over 3. So we rationalized it. Usually, guys, that's the best way to rationalize expression. Represent the exponent, the power, your radical and power, into a rational exponent. And then think what is missing to turn it into 1. Or to turn it into a whole number. It's not necessarily supposed to be 1. If you have, for example, here 5 over 3, you cannot turn it into 1. Or you can just multiply maybe by negative exponent to turn it into 1. You can turn it into 2 as well. No one really cares if the power of the denominator is the smallest power. You can make it bigger, like second power or third. Okay, I think that's going to be all for this lecture. And thank you very much. And I'm sorry for interruption in the middle for my broken screen, I think. Okay, and I'll see you next time.